let's think about the car. Just the car, okay? Now what I want to do, my real problem here, is that I have time and distances, and they're not really connected appropriately. See this? 40 kilometers per hour, that's related to time. But this 40 is not connected to time. It's a particular instance in the situation I'm thinking about. In fact, this number really should not be on my diagram at all. Okay, at least not in the way that they are at the moment. That kind of implies that that's 40 all the time, and that's 30 all the time. That's not useful. It's not a helpful way to label this diagram. I want this diagram to account for change. So the way I'm going to do that is to think about this guy. Now it's getting bigger, isn't it? Okay? It's getting bigger. Every hour that passes, it gets bigger by 40, right? It gets bigger by 40. So for instance, something I could call this distance up here, is 40t. Every time an hour passes, it gets 40 times bigger, right? Well, not 40 times bigger itself, but 40, 80, 120, and so on, okay? So that's a good place to start. This is much better. Calling it 40t is much better than calling it 40 because this thing's changing, which we know it's changing, right? Okay, good, but there's a problem with this, right? Which is that at time 0, where is the car? Now I can invent what time 0 is, right? But I might as well call it the starting point, which is when it's 40 kilometers away, right? So to account for that, I will add 40, right? So it'll start at 40, then it'll be at 80, 120, 160, rather than starting at 0, and then 40, and so on. Okay, so I'm calling this length here, right? I'm calling it 40t plus 40, right? Therefore, give me a name for the other length. 50t plus 30, right? To account for number 1, its speed, and number 2, its starting position, okay? Now what I've just done verbally is kind of what you would do by integration. So if you wanted to try and go with this, right? If I wanted to go from this, for instance, to get a statement for call that capital C, okay? Well, I could integrate, couldn't I? I could integrate this, with respect to t, which would give me this, right? But of course, you would get 40t plus a constant. Aha! How do we get rid of this constant? Initial conditions. And you would get your 40, and you would get your 30, okay? Now, this is a much better way to go, okay? Now when I call this x, because I have so much fewer variables flying around, right? I'm not going to run into this problem of how do I rephrase what in terms of what, and then what do I differentiate in terms of what, and so on, okay? What would I do here? I guess I would say, from Pythagoras, right, that x squared is equal to the sum of the squares of the two shortest sides. Okay, cool. Checked. Thank you. See ya. You can turn off that now, thanks. I've got an expression for x. It's in terms of time. Whoa, wait a second. This is really good because remember I said there's nothing wrong over this side, right? It's just awkward. But what I wanted, right? This can almost jump out directly at me. I don't need to worry about these guys anymore because I phrased them in terms of time from the beginning. Does that make sense? So it's kind of like a related rates question. Well, it is a related rates question, okay? But you don't have to phrase it that way. There are no related rates here anymore. I just have x and time, okay? So let's work with this. What am I going to get? I'm going to get 1600t squared plus 3200t plus 1600. Yeah, I check it out. What do I got here? 2500t squared. That's 1500. 3000t and 900. I've just written it on 2 lines to make the collection of like terms easy. Okay. Collect everything. 4100 of these, 6200 of these, and 2500 of these. That's a square. Okay. I can now get an expression for x, and I'm going to do 2 things at once. I'm going to take the square root, and I'm also going to take out the obvious factor, excuse me, of 100, 10 squared, right? So it'll be 10 out the front, and this. Of course, since I've only taken the positive value, I ought to explain why. And I can say x is 0, it's a length. Okay. Now at this point, I don't need to fuss around with any chain rule, which is what I was looking for before, because I have just x in terms of t. I already have x as a function of time, so I can just differentiate. Okay. This is to the power of a half. Can we do this in our heads? The half will come out the front. That'll become a 5, right? It'll go on the denominator because it'll become negative a half, so that'll be this. But of course, I also need to do the inside function, not just the outside. What's the derivative of the inside function? It looks like 82t plus 62. Yes? Okay. They ask us for a particular moment in time, namely after an hour. T's in hours, isn't it? I know I didn't define it, but you can see what's going on. So I say, let t equal 1, dx on dt. I believe you end up getting 720 on the square root of 128 when you stick 1 into all of these t's. Okay? So square root of 128, what's the biggest square number you can get out of that? I think it's 64. And I think that's... How many 64s is that? Sorry, it's how many 8s is in that, isn't it? Which is 90. 90. We're not that big a deal about rationalizing that kind of thing, but it just so happens in this case, I mean, that's a factor of 2, isn't it? So you might as well write this. Okay, and then you conclude 45 root 2 kilometers per hour at that instant in time. Okay? Can you see? Again, the calculus is not hard. It's all in the framing. Right? Once you get that right, it literally plops out. Not to mention, if you frame it right, changing the question a little bit doesn't throw you off. Okay? The next question, well, the next part of it says, at what rate would the distance between them be changing at that instant if they were both traveling toward the intersection rather than away? Okay, think about it. I've crafted my equations very well so that they would account for such a change very easily. What would be different if they were going the other way? This would not be 40t plus 40, would it? This derivative here, it should be going this way, right? The length is getting smaller. So therefore, this should really be negative 40t plus 40, still started at the same place. And this should be negative 50t plus 30. How is that going to change my derivatives as I go through? Okay, because there will be a negative sign here and here, right? It doesn't change these two terms or these two terms, does it? Because they've been squared, right? It changes these two. This will be a negative and that'll be a negative. So instead of plus 6200t, I'll get negative, which means I'll get negative there, which means I'll get a negative here and here. And then you can sub in the value. You will get dx on dt. I believe it's 100 on the square root of 4. I think. Just check out the numbers. Okay. Which of course is 2, that gives you 50. Ta-da! Okay. So, what did we learn? Okay. When you draw your diagram, yes, put on your information, but don't just do it blindly. Okay? Don't think, oh, okay, 40 here, 50 there, 40 and then 30, and then so on, right? Think about carefully how to build the rates of change into your diagram and therefore into your equations, because it simplifies it so dramatically. Okay? Does anyone clarify any of the steps? Does that look okay? Okay, all right. I'll leave that up there just in case some of you have not copied it down yet. But I think it's a really good question because it has related rates, but you don't need to think about it that way. Okay, and this is a really useful way to approach the kinds of lengths or volumes or whatever that you have changing on there. Okay.